Brim, and I worked in the electrical engineering department at Energy Systems Institute. Today's date is July 13th, and the topic of my research is the application of electrochemical cells. Okay, here's a brief overview. I'll talk about the electrochemical cell. I'll talk about my expectations from this research. I'll talk about my methods, results, and conclusion. Okay, first, an electrochemical cell is a device that just has a chemical reaction in it, and it changes that chemical reaction into electrical energy. And what I studied this summer was primary cells, which is basically batteries that cannot be recharged, and the chemistry in it is irreversible. You can actually reverse it, but it's not designed to do that. On the other hand, you have secondary cells, which are rechargeable, which my partner Antonio studied, and those you can recharge. Okay, basically what happens in the electrochemical cell is a reaction will happen right here. You'll have a half reaction, and the electrons from the half reaction will flow throughout the circuit, and then it will come back to the cathode, and you'll have a reaction that happens there, and then you have exchange of ions, and that will produce energy, electron flow right there. Some expectations for this research. My first goal was to characterize the battery cells. I wanted to understand which characteristics the battery cells have, so I know which applications they're used best in. And I also looked in ways to improve battery cells. Actually, I looked into a battery cell called lithium air, and I looked to get it, but actually it's not able to be created yet because there's problems with the chemistry. But it's research that's being looked on by a lot of scientists today. And I also want to look at adequate sources for power in future technology, such as electric cars, hybrid cars, phones. That's like Nico said earlier, phones are getting smaller, and they're needing more energy, and the things that phones are doing are becoming a lot greater. Just a little bit on my methods. I had 3 basic methods to characterize these batteries. First, I wanted to weigh them to get accurate mass. Then I tested internal resistance and generated discharge curves. First, I wanted to weigh the battery because it was very important for the energy to mass ratio, and in that I get the energy density, which plays to be an important factor in this research. The second test included an internal resistance test. Basically, what we did was there's a small resistance in the battery. We researched the resistance in there, and we tried to get a resistance to match it up. And what that did was that allowed us to come up with a formula, which is right there, because we had the open circuit, the open circuit voltage, and that allowed us to calculate the resistance across the circuit right there. My third method was to generate a discharge curve. The discharge curves, it plotted time against voltage, and the area under the curve gave us an analysis of the energy produced by the battery. And from there, you could also calculate power, and that's what the main purpose of the discharge curve was. I used 2 different methods to generate a discharge curve. The first one was using this system right here, a computerized battery analyzer, and that plotted points that was connected to a computer every second with a constant current flowing through it. And the second approach I took was using a data logging circuit. And this, I created a circuit with basic resistors discharging, you see one right there, one right there, and one right there. Those resistors discharged the battery, and it seemed to discharge at a slow rate, but at one point it dropped off, and that recorded along the computer also. This is some results I have. This was the first curve for alkaline batteries. This was using the computerized battery analyzer because it has a constant current. As you can see, it's a nice little slope. The battery starts off fast and it levels off and it goes down quick. What you notice in alkaline batteries, our discharge curves aren't as flat as the other ones. I'll show later. This is a lithium iron disulfide battery. I also discharge this at a constant current. I discharge this at 2 rates to test how different rates affects the capacity. Right here, this battery right here reached a little more than its full capacity because I discharged it slower. However, when I discharged it at a faster rate, it dropped a little short. That's why you see differences in the curves right here. Here's another discharge curve I did, and this was the circuit I created. I did discharged all these simultaneously, and as you can see, zinc air battery, it lasted the longest, therefore it produced the most energy. And these other batteries right here, the slope wasn't as, and lithium manganese, the voltage starts off high, but the slope wasn't as flat as zinc air, so it didn't last as long and it dropped off. And for silver oxide right here, the battery, it seemed to last a long time initially, and the slope was pretty flat, but then it dropped off immediately. This right here is the zinc air battery that I discharged at a constant current, and right here you see that the slopes are pretty flat also, and it reached a little more than its full capacity because I discharged it at a slow rate. Right here it appears to be a distorted zinc air discharge curve with a constant current. The distortions is due to a number of variables in my testing. After I graphed this, I looked into different variables, and as you can see, it goes up and down and up and down and up and down instead of the constant flat discharge curve I was looking for. Once I looked into it, I found out that, as I'll say in my next slide, that humidity levels play a major factor in it. As you can see right here in this graph right here, it's a graph from the Dorsal site. It shows that higher humidities definitely affects it compared to lower humidities. As you can see, 30%, it's a more flat curve. It's not a lot of humidity going on, but when it's 90%, the humidity temp appears to rise and it drops off a lot quicker. And the air holes in zinc air batteries, there's air holes because air is is part of the cathode, and the zinc air battery draws the air in used for the chemical reaction. So if these holes are plugged up and aren't used to its full potential, then the battery won't perform as expected. And temperature is another major factor. As you can see in this graph right here, zinc air definitely needs a specific temperature to perform at its peak. And we performed our test around room temperature, which is around 21%, and that didn't really change that much. But however, day to day, the temperature did change, and that affected my test a little bit. So the second time around, I created a more controlled environment, and it gave me a much flatter curve. These are some results that I got, and I just made a table. Right here is just a list of all the capacities, and these are the capacities that I tested and what I found out what I figure out the capacities to be. When it's higher, that means I drain the battery at a slower rate than is recommended to be drained at. So I reached the capacity and beyond it, as I said before. When in some cases it may reach to be a much lower capacity, like the zinc air at 8.4 volt. That means I drained the battery too fast, and some batteries aren't meant to be drained as quickly as others. Here's a Ragone chart, and this chart, it plots energy density against power density. And as you can see, high up here you have the lithium iron disulfide batteries. And far to the right you have zinc air batteries, and that's why I expected, because zinc air is known for its energy density, and zinc air is you also look to put zinc air in things, devices that need to last a very long time. And as on the other hand, you might want to use lithium iron disulfide batteries for batteries that you need to drain things quickly and need a lot of power. And this chart right here shows you a good idea of what applications you should use batteries in. For example, right here, alkaline batteries, they're far on the left and they aren't too far up on the power side. It's not that it's a bad battery. It's you have to definitely consider what applications you want to use this battery for. For example, if you don't want to use something for a very long period of time, like a remote control, doesn't need high power or a long energy density, you might want to use that. It might be better worth your payments. However, you can't use this battery for something that needs to be ran for a very long period of time. This is why zinc air batteries are used in medical devices, because they need to be constantly running. And future research, I'm looking to research lithium air batteries and further research that, and because that's a big topic, because lithium is a chemistry that's very high on the power density charts, and the air that's drawn from it is it's also another thing that that is far on the right on the compared to the Rugoni chart, it's far on the right, so it gives you a high energy density and a high lithium density also. And I'm also looking to put what I research into applications. For example, put them in devices to see how that tests out. And I'm also looking to make a big chart of more chemistries to research. And here are my references. And here are my acknowledgments. I'd like to thank my mentor, Dr. Jennifer Zernheld, my graduate students advisor, Daniel Muffaletto, the CSTEP program, Shauna Crump-Owens, director of CSTEP, Energy Systems Institute, and my undergraduate students that were my partners, Antonio Yupia and Michael Sparks.
You said you tested the batteries at room temperature, right?
Yes.
Is that a must? Like, you have, like.
It's not a must, but it's a recommended thing. For example, like if you paid attention to the chart I showed on there, you saw how different batteries, like the range that you wanted to get it in was around 20 degrees Celsius to around 28, and sometimes it was hard for me to keep it in that temperature because I had to solder batteries together in order to get a connection to the test I was making, so I tried to keep it in that general temperature.
When you were talking about weighing the batteries and doing that in order to get the energy density of the battery, were you weighing the actual chemical component of the battery or the whole battery?
The whole battery, and that's another thing. That's where some sources of error could come from, where exactly it might not be the same number that I researched. Because, for example, if you have the zinc air battery, it's a lot more plastic casing around the actual battery instead of a small button cell battery. So I might get different numbers when I test out the energy density.
So you're trying to get the energy density based on the weight of the battery. So if I'm carrying this battery, I know how much energy I'm getting for the weight that I'm carrying, not for like the chemical component where the energy density of the actual chemicals in there.
Yes.
Okay.
Any other questions?